Now let's talk a little bit about the general theory of linear systems of differential equations, about things like the Wronskian, solution space, and so on. I think it's easiest to understand if I immediately illustrate it by an example. Right? So here is my example, and this is how you can write it down in the matrix form. So the coefficients are, so notice that this t is here, there is -1 which is here, there is no x in the front in the first row, so 0 here, then there is x here, its coefficient is 1, and so on, right? Now, how do we solve systems of linear equations with non-constant coefficients? So notice that here, right, so t is present in the right-hand side, and if t is present, it means that the coefficients are non-constant, but there is no free part, so there is no plus something, so which means that it is a homogeneous system, at least. How do we solve such systems of differential equations in general? Well, there is no way. The reason why I know how to solve this system, because I invented it. So I just when I prepared my lectures, I just thought of some simple system with non-constant coefficients that I know a solution of, and I just invented it. But even inventing such a system was not easy, believe me. Well, anyway, so I succeeded, so at least we can check the logic. So for example, we can verify that these equations 1t and t square as x, y, and z respectively, they give us a solution. So we just substitute them into the system of equations, and then we see that we get all the true equalities. Then we have another solution and one more. So each solution, so it contains x, y, and z, so meaning that it is a vector, right? So we have 3 vector solutions. On the other hand, since we have 3 unknowns and 3 equations, so 3 means that we have the solution space is a vector space of dimension 3. And at the same time, we have found 3 solutions. So in order to ensure that these solutions do generate the whole solution space, which means that every other solution is going to be a linear combination of these 3, we need to compute the Wronskian to see if they are truly linearly independent. And again, for vector functions that are solutions of the same system of differential equations, it is true that the Wronskian is either never 0 or is always 0. So if the Wronskian were just 0, then we would conclude that x1, x2, and x3 are linearly dependent. And here, so generally speaking, the Wronskian, so notice that the Wronskian contains t here. So generally speaking, we cannot expect that it's always going to be a constant. It just happened to be now that it is a constant, but it doesn't have to be. The general theorem is that the Wronskian, even if it is not a constant, then it is either always positive, always negative, or 0. So it cannot have be sometimes positive, sometimes negative. I'm sorry. So the general solution of the system is going to be a linear combination of these 3 solutions. So again, we have 3 equations and 3 unknowns. It means that the solution space has dimension 3. Since these 3 solutions are linearly independent, I conclude that they do generate the whole solution space. Well, that's the general solution. Suppose that we want to solve some initial value problem, right? Then we just substitute the value of t, which is 0 here, and then equate the left-hand side to the right-hand side, and then we can solve for the coefficients.